Okay, we're talking about chapter 15, last chapter. This is the one dealing with statistics. We're talking about inferential and descriptive statistics. My son called. That's why that's why we didn't finish this chapter. Okay, but good news. He has had a job offer in North Carolina, and he's got a second job offer. So he gets to choose between a public school and a private school, looks like. So we'll see what happens. Both descriptive and inferential statistics help social scientists develop explanations for complex social phenomena that deal with relationships between variables. Statistics provides the tools to analyze, represent, and interpret those relationships. After data have been coded and prepared for processing, they are ready for analysis. The researcher's first task is to construct frequency distributions to examine the pattern of response to each of the independent and dependent variables under investigation. A frequency distribution of a single variable, known as an univariate frequency distribution, is a table that shows the frequency of observations in each category of a variable. To construct, the researcher lists the categories of the variable and counts the number of observations in each. Nominal variables may list the categories in any order. For the variable gender, either category male or female may be listed first. It could be male or female or male. It really doesn't matter. Ordinal variables represent different rankings. Ordinal variables must be arranged in increasing or decreasing order. Interval variables are ordinarily continuous. The intervals are usually of equal width, but the width depends on both the number of observations to be classified and the research purpose. The larger the number of observations, the wider the intervals become. However, wider categories also result in greater loss of detailed information. This is the Scoville-Chilly heat chart on the right. Really kind of curious. I cannot eat most of these. My daughter was complaining the other day about her neighbor keeps offering her habaneros. They're 200,000 to 350,000 heat units on the Scoville scale. As you can see, it's one of the hottest peppers that are out there. She says that she would eat all the jalapenos in his garden if he would just grow jalapenos, but no, he has to grow habaneros. And of course, she can barely tolerate one. Jalapeno, she eats jalapenos all the time. To facilitate comparisons, researchers convert frequencies to proportions or percentages. You obtain a proportion by dividing the frequency of the category by the total number of responses in the distribution. When multiplied by 100, a proportion becomes a percentage. Proportions are usually expressed as frequency divided by the number, and percentages as frequency divided by the number times 100. Both proportions and percentages reflect the relative frequency of a specific category in the distribution. And there we go. So frequency is 3, total number is 20, so you divide 20 into 3, and you get 15%. That's blue, or whatever. 3 commonly used graphs are pie charts, bar charts, and histograms. Both the pie chart and the bar chart can be used to present data measured at the nominal and ordinal levels. Researchers use the histogram to display data measured at the interval or ratio levels. And this is this is what they look like. The bar graph is this is the line graph. This is the pie chart or circle graph. Histogram and the bar graph, and this is a stem. You can't see what I'm doing. Okay, wait a minute. Okay, this is the bar graph. This is the line graph down here in the middle. This is the pie chart or the circle graph. This is a histogram, and this is the stem or leaf plot. Okay, there we go. There you saw what I was talking about. Pie chart shows Differences in frequencies or percentages among categories of nominal or ordinal variables by displaying the categories as segments of a circle. While one pie chart can be used to represent a single distribution, researchers often use two or more pies to compare distributions. What do we have? So we have the Los Angeles Lakers, the Minneapolis Lakers have 22% of the NBA championships. The Celtics have 24%, and all others have 31%. San Antonio Spurs 7%, Chicago Bulls 8%, and Philadelphia, San Francisco, Golden State Warriors have 8%. There you go. So I guess the winningest team in NBA history is the Boston Celtics. Bar chart is a tool for displaying nominal or ordinal data. Two or more distributions may be presented on a single bar chart. Height of each bar is proportional to the frequency or percentage of the category. It may be displayed either horizontally or vertically. And I'm not sure what that is about. Okay. Histogram display frequency distributions of interval level or ratio level data. Histogram looks like a bar graph with no spaces between the rectangles. Obviously, before I got this is your bar chart. No, this is your histogram and this is your bar chart. I got them backwards. I apologize. Okay. Rectangles are constructed contiguously to show that the variable is continuous, and the intervals rather than discrete categories are displayed across the horizontal axis. Unlike the bar chart, the histogram cannot be used to display information for more than one variable. And of course, that's a histogram. Measures of central tendency are statistical measures that reflect a typical or an average characteristic of a frequency distribution. The three measures social scientists most commonly use are mode, median, and arithmetic mean. Mode is a category of observation that appears most frequently in the distribution. Mode is used as a measure of central tendency, mostly with distributions of nominal variables. You identify the mode by singling out the category containing the largest number of responses. And on the right, of course, it would be 6, because there are 3 6s and there are 2 3s and 2 9s. So the mode is 6. The advantage of the mode: it's easy to identify by inspecting the frequency distribution. Therefore, it can be used as a first and quick indicator of the central tendency in the distribution. The limitation: it is a sensitive indicator. Its position can shift if the researcher changes the way the distribution is divided into categories. Therefore, it is not a very stable measure of central tendency, the mode. The median is a positional measure that divides the distribution into 2 equal parts. Median is defined as the observation that is located halfway between the smallest and the largest observations in the distribution. So you have to list them all in order, and then the one in the middle. And if it's an even number, then you have to divide the two middle numbers. You have to divide them in half. You have to add them together and divide them by 2. If it's an odd set of numbers, like this one has 7, so it's the 4th number, is your median. Mean is the most frequently used measure of central tendency. It's suitable for representing distributions measured on an interval level or ratio level, and lends itself to mathematical calculations. Mean also serves as a basis for other statistical measures. Mean is defined as the sum total of all observations divided by their number. So if you add up all the numbers divided by the number of units, in this case, all those numbers add up to 105. Divide 105 by 7 and you get 15. 15 is the mean. In symbolic notation, the mean is defined as x bar equals the arithmetic mean. sigma x is the sum of total observations. This thing is a sigma, and that means that you add everything up. You add up all the x's. And then n is the number of observations. They call this an x bar, as weird as that sounds. Unfortunately, in my in the statistics book, I've been working with statistics this summer. It calls it it's a y bar in there instead of an x bar. As confusing as all that is. So, but let's call it an x bar. We'll pretend that that doesn't exist. X bar equals sigma x over n, and that just means you add up all the units and you divide by the number, and that gives you the arithmetic mean. Range measures the distance between the highest and lowest values of the distribution. For example, 4, 6, 8, 9, 17. The range is the difference between 17 and 4, which of course is 13. The range is useful for gaining a quick impression of the data, but it is a crude measure of dispersion because it only accounts for the two extreme values of the distribution. So if you were looking at the wealth of Navajo County, you might have one family that makes $4,000, and you may have some billionaire that moved into the county and bought a ranch on, I don't know, maybe some Navajo who rodeos made $1 billion off of rodeoing. So he moved to Navajo County, and so he's got $1 billion. The other person has $4,000. So what's the range of the incomes in Navajo County? Well, it would be very large. It would be huge, but the reality is that wouldn't really give you very good information as to the distribution of incomes in the county because of that billionaire would skew the results. As weird as that seems. Interquartile range, difference between the lower and the upper quartiles. Because it measures the spread of the middle half of the distribution, it is less affected by extreme observations. The range can also be calculated for other measures of location. Example, you can calculate the range between the 10th and the 90th percentile to measure the dispersion of the middle 80% of the observations. Normally, see, this would get rid of all your skewed data by just looking at the interquartile range. So if we had that person that made $4,000 and the person that made $1 billion, since he's the only one that makes $1 billion in Navajo County, and we would take out all the really wealthy people, and we take out all the really poor people, we just have the people in between. So your interquartile range may be between $28,000 and $60,000. So the interquartile range would be $40,000, which makes a whole lot more sense than what? $999 million as your range. That doesn't make any sense at all. $40,000 would be a lot closer to being correct. And as you can see, this is the way it works. There's your median. Okay. Deviation, the simplest way to obtain a measure of deviation is to calculate the average deviation from the mean. The average deviation equals sigma times x minus x bar over n, where x equals the individual observations, x bar is the arithmetic mean, and n is the total number of observations. However, the sum of the deviations from the mean is always equal to 0. Thus, the average deviation will be 0, for its numerator will always be 0. To compensate for this property of the mean, we square each deviation to calculate standard deviation, the measure of dispersion most commonly applied to interval-level data. The simplest way to obtain a measure of deviation is to calculate the average deviation. Wait a minute, I went the wrong direction, didn't I? Yes, I did. Variance and standard deviation are calculated by squaring this and summing the deviations, then dividing the sum by the total number of observations. The definitional formula for the variance is s squared equals the sum of x minus x bar squared divided by the number, where x is the variance. X squared is the variance. In other words, the mean is subtracted from each score. The differences are then squared, summed, and divided by the total number of observations. To calculate variance, the squared mean is subtracted from the squared sum of all scores divided by the number of observations. And you can see how that works. The square root of the variance transforms the variance into the standard deviation. So if you know the variance, you can get the standard deviation just by taking the square root of whatever the variance is. The standard deviation is a measure of expressing dispersion in the original units of measurement. When data are arranged in frequency distribution, we can use the following modified formula to calculate variance. And as you can see, we're starting to get into a lot of different letters. The advantages of standard deviation: it is more stable from sample to sample. It has some important mathematical properties that enable the researcher to obtain the standard deviation for two or more groups combined. Its mathematical properties make it a useful measure in more advanced statistical work, especially in the area of statistical inferences. Symbolically, the coefficient of variation is defined as follows: V equals S over X bar, where V equals the coefficient of variation, S the standard deviation, and X bar equals the arithmetic mean, just like it has meant before. The simplest way to describe a distribution is by visual representation. It can either be symmetrical, it can be negatively skewed to the right, or it can be positively skewed to the left. Goodness gracious. In non-symmetrical or skewed distributions, there are more extreme cases in one direction of the distribution than in the other. A non-symmetrical distribution in which there are more extremely low scores is referred to as a negatively skewed distribution. When there are more extremely high scores, the distribution is positively skewed. Most income distributions are positively skewed, with few families having extremely high incomes. Skewness can also be identified according to the positions of the measures of central tendency. In symmetrical distributions, the mean will coincide with the median and the mode. In skewed distributions, there will be discrepancies between these measures. In a negatively skewed distribution, the mean will be pulled in the direction of the lower scores. In a positively skewed distribution, it will be located closer to the higher scores. The normal curve has great significance in the field of statistics. It is symmetrical and bell-shaped. The mode and the median and the mean coincide at the center of the distribution. The curve is based on an infinite number of observations. A single mathematical formula describes how frequencies are related to the values of the variable. In any normal distribution, a fixed proportion of the observation lies between the mean and fixed units of standard deviations. And that's what a normal bell curve looks like. This is what we were hoping would happen with COVID-19. We were hoping that we would slowly reach the peak, and then we would slowly decline. And that's why we wanted to lower this curve as much as we possibly could, because we knew that after we had it increase, we would have a slow decrease, and then it would finally go away, just like the flu does every year, just like winter colds go away after every year. But of course, COVID-19 has proved that it is not a normal distribution. And of course, that's what people were saying from the very beginning, that this might not. It all depends on a lot of different things. Statistics will tell us one thing, but and of course they were predicting, geez, how many people are going to die? Now they're saying that we'll be up to 175,000 by the middle of August, 175,000 deaths. Right now we're at 140, close to 147,000 deaths, and they're saying within the next 20 days we're going to have the next 3 weeks we're going to have 13,000 more deaths. That's the prediction. But of course we're hitting the. They predicted that by the end of this month we would have 142,000, and we're already at 147,000. We still have a week to go. So predictions haven't been very good lately, mainly because they have to predict looking at what's going on in the world, and the assumption was that if people social distance and they wear their masks, then we should be right around 142,000. But instead, people have used it as a political football, and so people aren't wearing the masks and they're not social distancing. Of course, this isn't happening on the Navajo Nation, but it's certainly happening in other places. People are rebelling against the mask, as weird as that is. So the numbers is going up because their predictions were based on people social distancing and wearing masks. Researchers can use a normal curve to evaluate the proportion of observations included within a desired interval. The raw scores must be converted to standard deviation units to use the table, which reports areas under the normal curve. When raw scores have been converted to standard scores, a single table can be used to evaluate any distribution regardless of the scale on which the data were measured, and distributions measured on different scales can be directly compared. We got a problem right now. They're going to open the schools up again, and of course the idea was that we would flatten the curve by this time and we would be on our way down. But that's not what's happening. But they're going to open the schools anyway because people aren't smart enough to figure these things out. The people in charge in this case are not smart enough to figure these things out. So they're opening the schools despite the fact that there's a lot of potential dangers in opening the schools. We don't know what it's going to do to the children. Right now, the COVID-19 doesn't seem to affect anybody under the age of 10, but over the age of 10, it affects people just as much. So if you've got somebody that's older or somebody that has medical issues, then potentially what will happen is the children will bring the virus home, and we will have it. And COVID-19 will kill more people. But these all have to do with statistics. And of course, a lot of people like to say that there are good statistics, bad statistics, and then they swear about how bad statistics are. Observations are converted into standard deviation units by means of the following equation: z equal x minus x bar over s, where z equals the number of standard deviation units, x equals observation, x bar equals the arithmetic mean, and s equals the standard deviation. So you divide the standard deviation into your observations minus your arithmetic mean, and that gives you your z-score. Z, sometimes referred to as standard score, expresses the distance between a specific observation and the mean in terms of standard deviation units. Standard deviation units, if somebody is in the middle of the bell curve, whoops, there we go. If somebody is in the middle of the bell curve, they are 0 standard deviations away from the mean. If they are 1 standard deviation away, as you can see, they're 31.6%. They represent 31.6%. That's 1 standard deviation. This is 1 standard deviation. This is 2 standard deviations, as you can see. So when you took your SAT score or your I don't know, Iowa Basic, whatever, they told you how many percentile you were. Well, if you were in the 85th percentile, you're way over here. You were 3 standard deviations away from the mean. If you were in the 50th percentile, you're right here in the middle. Okay, so depending on on how high you scored, you could be 1 or 2 or 3 standard deviations away. As weird as that seems. I've already told you, we had, when I was going to high school or in grade school, we had a bunch of really bright kids in our class. So our statistics were really skewed to the positive side because we had so many kids over here, and it kind of messed everybody else up. It really messed them up. It's like taking a test and he curves the grades, but so many people scored so high that even though you got 90%, it was still one of the lowest grades in the class. Now, he'd probably still pass you if he's a smart guy. But once upon a time, when people went to Harvard University, they would compare. You were compared with your cohorts. So if everybody else in the class did really, really well and you did mediocre, you might flunk the class, despite the fact you would have passed anywhere else, because that's the way they did things back then. Hopefully they don't do that anymore. I don't think they do. Z, sometimes referred to as standard score, expresses the distance between a specific observation and the mean in terms of standard deviations. Standard deviation units, a z of 2 means that the distance between the two, the mean of the distribution, and x is 2 standard deviations away from it. And that is the end of the chapter. So we are done. We're done for the summer. You have to have everything in by Friday. That would be nice. If you need more time, email me, and I will hold off on completing your grades. I have to have them turned in by Monday. So let's get everything in. Let's all do well. Let's all pass this thing. I'd hate for you to have to do this again. I will not be teaching research methods or statistics. I kind of taught statistics this summer, but I won't be doing it. Again, we have hired somebody to teach statistics. Dr. Suzanne Russ is our new statistics and research methods person. So too bad you guys got me. I tried to stay away from this class, but both Dr. Wolf and Dr. Kine quit at the same time at the end of last year, and we didn't have anybody to teach the class. So I got roped into it, unfortunately, as sad as that is. But we're done. We're finished. So I love you guys. Stay safe. I'll see you. Well, I won't see you. Maybe I'll see you on the video. But oh no, where did my thing go? It's gone. Oh, it's right here. Okay.